Okay, we're going to start talking about what we call bicyclo compounds. Bicyclo compounds are where you have two rings that are joined together. If I look at these two rings, you can see there's two rings, one here and one here. These are called fused rings because there are no carbons between the carbons that join the two rings. So these are fused rings, and this actually has a common name called decalin. This you can see is called transdecalin, and this one would be called cisdecalin. That's just because the hydrogens and the carbons point in on opposite sides of the ring. You can see this is up, that's down, this carbon is up, this carbon is down, so it's trans. If I look at this, you can see the two hydrogens are up, and notice that carbon's down, so this is cis. You cannot interconvert these because you have to break a carbon-carbon bond. We actually find there's more steric strain here in diaxial interference than with this ring, and so this ring, transdecalin, is more stable than the cisdecalin, which we usually think of cis as being more stable intuitively, but you can see trans actually is more stable here. This compound has 6 carbons in the 2 rings. There's one ring here that has 5 carbons in it and one ring that has 4 carbons in it, but they have carbons that are in common. So what we do is we look and count what are all of the carbons in the rings only. So there's 6 carbons. So this is going to be called a hexane. If I need to also count how many carbons are in the bridges. The bridgeheads are the carbons that are in common to both rings. The bridges are the carbons that go from one bridgehead to the other. So there's one bridge that has 2 carbons in it, one bridge that has 1 carbon, and another bridge that has 1 carbon. So I actually will say there's a 2, 1, and 1 bridge in this compound. And then this is how we go to name it. I start with the name bicyclo. Then I say how many carbons are in each of the rings, starting with the bigger bridge first. I say 2, 1, 1 for the bridges. And then I end with hexane because there's 6 carbons in it. So I'm going to ask you to try to do this. You're probably going to make a mistake the first time. Don't worry about it. You'll learn it. But you go ahead and name this one in the same method. This is a bicyclo compound, so name this as a bicyclo compound, and then restart the lecture to find out what the answer is. Okay, to name this, the first thing I would do is count all the carbons in it, and you only have 4 carbons, so this is going to be a butane. So we write butane down first. Then we look to see how many carbons are in each of the bridges. There's 0 in this one, and 1 in this one, and 1 in this one. So we're going to say 110 for the bridges. And then we put bicyclo in the beginning. So bicyclo 110 butane. Go ahead and draw a constitutional isomer of cis 1,2-dibromocyclopentane. Remember, there's more than one possible answer here, so don't let it bother you. No, there isn't. There's only one possible answer. But go ahead and try and figure out what would be a constitutional isomer, and then draw the stereoisomer of this. So it's a 2-step problem. Pause it, and then restart when you've gotten your answers. Okay, the answer here is that if you drew a 1,3 isomer as a constitutional isomer of 1,2-dibromocyclopentane, then you have the correct answer. It could be either cis or trans, and what you probably would want to do is not indicate cis or trans at all, but just draw straight lines for the bromo, and that would be fine. Stereoisomer of cis 1,2 has to be the trans 1,2. So this is the stereoisomer of the cis 1,2. Go ahead and determine which of these is more stable. Okay, if I look, this and this are equatorial, and this are axial. Axial is less stable than equatorial. However, this is axial, that's equatorial. On this A, what you see are 2 axial and 1 equatorial, and on B, what you see are 2 equatorial and 1 axial. So this structure on the right, A, is less stable, B is more stable. Okay, which of these drawings on the left, of those 4 drawings drawn in a chair conformation, is the most stable conformation of this cis 1-methyl 4-isopropyl cyclohexane? Okay, if I go and I look at these structures, I can see this is axial, this is equatorial, and that is axial. The isopropyl group is bigger, so that's good to have it in the axial position. Is it cis? Yes, it's cis, because both are down. If I look at this, this is trans, so it can't be it. If I look at this, this is cis. But the methyl is equatorial, and the isopropyl, which is bigger, is axial. So that's not very stable comparative to this one. If I look, both of these are equatorial, and you might say this is most stable, but it is not this conformation over here. I mean, this structure here. These are cis-trans isomers. This is cis, and that is trans. So this is not that compound. This one right here, which has the isopropyl equatorial. Okay, so what is an IUPAC name for the following molecule? Is a cis isomer. Figure out which one is the correct name. More stable conformation. Okay, if I look, this is the correct name. Let's look and see why. This is a cyclopentane here. Attached to the cyclopentane is a 1, 2, 3. That's the longest chain of that attached. So that is a propyl that is attached that has 2 methyl groups on it. So let's go ahead and see how that is. There's a propyl, and then the 2 methyl groups are right there. Now, we always number our propyls from the carbon that is attached. We always number our alkyl groups by the carbon that is attached to the ring. So let me get a pointer here for you. If I look at this carbon right here, this is the number 1 carbon because it's attached to the ring. So that's the number 2. So when I go to name this, I'm going to say that's 1,2-dimethyl is the substituents on the propyl. But in order to make it so that this is considered to be an attachment on the cyclopentane ring, I put a parentheses around the 1,2-dimethyl and propyl, and then put dash cyclopentane. If I put 1,2-dimethyl propyl cyclopentane without the parentheses, someone would think that the 1 and the 2-dimethyl were on the ring and not. So how many secondary hydrogens are there in this cycloalkane shown below? Okay, if I go and I look for a secondary hydrogen, it's going to be on a carbon that has 2 carbons attached and 2 hydrogens attached. And all the bridgeheads here, there's a lot of them, all have just 1 hydrogen attached and 3 carbons attached. So they're tertiary. Right here and here are the secondary carbons. So we see there are 2 of them. That's wrong. 2 carbons. 4 hydrogens. My bad. Goes to show you got to read carefully. Okay, on this one, I want you to go ahead and figure out on this 6-membered ring, this is just like a cyclohexane ring, and that has axial and equatorial positions. So go ahead and figure out, if I look at the groups on this, okay, and so I'm looking at this group, this hydroxymethyl group is right here, and this group right here, this is, well, don't worry about what type of group it is, but this group right here, this alkoxy group, okay, if I look at this and this, how are these relative to that amino group? Are they cis or are they trans? Remember to think up and down in order to figure out, are they cis or trans? Try to place your hydrogens, the other group on the carbon, in an up or down position, and then figure out, is those particular groups up or down, and how are they relative to the amino group? Okay, if I look, this amino group is down. This group, not the hydroxy here, but the carbon right here, is up. There is a hydrogen going down here, and there is a hydrogen going up there. So this amino group is down. This carbon right here is up. So they're trans. If I look at this group, it's up because there's a hydrogen that is going down axial. So this is up compared to the amino group, which is down. So it's trans. So both of those groups are trans. Okay, and this is showing this one's up and that one's down, so they are trans. All right, what kind of strain is relieved the most by ring puckering in cyclopentane? If I think back, the cyclopentane, if it was flat, has almost no ring strain. It puckers in order to relieve torsional strain. Which of the above molecules represents the most stable conformation of trans 1,3-dimethylcyclohexane? If I go and I look, I can see that there would be a hydrogen up here and a hydrogen down here, so this is trans. There's a hydrogen up here and a hydrogen up here, so this is not trans and we don't consider it. There's a hydrogen up here and a hydrogen down there, so this is trans, but this is 1, 2. This one is 1, 4, and so it is not 1, 3. If I look at this and this one's 1, 4, so it's not that. If I look at this is a 1, 3, and if I see I have one axial and one equatorial, hydrogen up here, so that's down, hydrogen down here, so that's up, and so it's trans. So it's trans 1, 3, and this is doing what? One group axial, one group equatorial. There's no other 1, 3 there, so it has to be the most stable. But even if you were to flip the ring, you would not change the axial number of axial positions. You'd still have one axial and one equatorial. Okay, which of the following does not contribute to the overall energy of a cycloalkane? Okay, if I looked at all of the cycloalkanes that we looked at, we considered both torsional, angle, and steric strain. So those all contribute. But we didn't talk about hydrogen bonding at all. In fact, cycloalkanes cannot hydrogen bond because there's no oxygen or nitrogen in them. So this cannot contribute to the energy of a cycloalkane. Which of the following statements are true? Which of the following statements are true? Okay, so now which is true about the isomers cis-1,2 and cis-1,3 dimethylcyclohexane? Okay, if I look at this, the only one that is true is that the favored conformer of the 1,3 isomer is more stable than that of the 1,2. Why is that? Because the 1,3 cis can be both methyls in the equatorial position, whereas 1,2 cis has to have one in an axial position at all time. So they are not constitutional isomers. That is incorrect because they are. It's 1,2 versus 1,3. They represent different conformations of the same molecule. They're different molecules, so they can't. The 1,3 isomer and that of the 1,2 isomer are equal in energy? No, because 1,3 can have both of them equatorial, and 1,2 has to have at least one axial, or one equatorial and one axial. And the relative stability of the two molecules cannot be determined. Well, that's not true, because we went through a lot of talk about how when it's 1,3, one can be axial, they can both be equatorial or both axial, and 1,2, one equatorial and one axial. If you're having trouble determining the stability of the two molecules, try drawing them out and putting them in various positions to try and figure out which one is more stable and which one is less stable. Okay, if I look at this, which of the isomers right here is represented by this Newman projection? Figure out which it is. This is relatively easy. You can see that one is up, and there are some other up and down positions which are axial, and then one is in the equatorial position to the right, and so this one's equatorial, this one's axial, and these are the other equatorial positions right here. And this is 1,4 because this is 1, 2, 3, and the one in the back is 4. Okay, which of the above structures represents the most stable conformation of 1-tert-butyl 3,5-dimethylcyclohexane? Remember, a T-butyl group is a carbon with 3 methyls attached, so it looks like the crowfoot up there. Okay, if I go and I look, this is not 1,3,5, but 1,2,3. This is 1,3,5, and it is, if I look at this, you would have T-butyl right here is 1, then on 3 you have a methyl, and on 5 you have a methyl, but notice they're all axial. If I look at this, this would be 1, 3, 5 again, but they're all axial. If I look at this is 1, 3, 5, they're all equatorial here. That's good. If I look at this is 1, 3, 5, but notice two of them are axial. The most stable conformation of 1, 3, 5 would be where they're all equatorial, which is this position. What happens to a substituent in a chair conformation of cyclohexane when all the bonds rotate in a synchronized fashion? All these bonds rotating in a synchronized fashion means flipping the chair. So a substituent, when the chair is flipped, does what? Axial becomes equatorial and equatorial becomes axial. Okay, which of the structures above will have the highest energy after a chair flip? So look at one and figure out which will be highest energy after a chair flip. So if I look at this, these two are equatorial, so they'll both become axial. These two are equatorial, and they'll both become axial. This one right here goes from one axial to one equatorial, to one axial and one equatorial. Both here will become axial on a flip. And here you would have one axial and one equatorial after a flip. So of these three, those would have the highest energy after a chair flip. Now, if I look, this would be 1, 4, this is 1, 3, and this is 1, 2. Which has the highest energy after a chair flip? Well, all of them are going to go into axial, but which has the greatest steric hindrance between groups? These are pretty far away. These are going to be close through the air. They're going to have a 1-3 diaxial interaction. Here, they're going to go from being gauche to anti. So if I look, this one right here will have the highest energy after. What are the relative geometries of the ring fusions here? Cis, trans, whatever. Look at the rings and try to figure it out. If I look, I will see that this one's cis, and then the hydrogen down and one up, trans, the methyl up and the hydrogen down, trans, so it's cis, trans, trans. Okay, go ahead and try to name this compound. If I name this compound, the first thing I'm going to do is count all the carbons. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be an octane. It is bicyclohexane, but now I have to count the numbers in the bridge. If I look, there are 3 bridges with 2 carbons each. So this is going to be bicyclo, not bicycle, my apology, there's a typo there.